Welcome to another very important lesson that we're going to look at today. Basically today we are going to look at linear momentum. By the way, my names are Siamasaka, Kilian Dens. And so I will take you through linear momentum today. Basically we'll discuss the concepts in linear momentum. And so I plead with you that you pay particular attention, because if we understand the basic concepts, then whatever we're going to do later on in the application of these concepts, it becomes very, very easy. And therefore, I invite you for the lesson for today. So as I indicated, actually linear momentum is the actual product of mass and velocity. And so when you talk of linear momentum, you are talking of that you are actually multiplying the mass and the velocity of an object. And so we are aware that from Newton's second law of motion, we are aware that force is equal to mass times acceleration. And this acceleration is given by final velocity minus initial velocity over time. So where there is acceleration here, you can substitute this acceleration, which is given by final velocity minus initial velocity over time. And so if you multiply it, time multiplied by force, which we have done here, it means that we're going to remain with the mass in brackets final velocity minus initial velocity, which is this one. And this term, force multiplied by time, is what is known as the impulse of a body. So actually, what this means is that the impulse of the body is actually the change in momentum. So momentum after minus momentum actually before. So in other words, we are saying the final momentum minus the initial momentum. That's what is known as the impulse. Normally, when an object hits into a body or it collides into a body, we would always want to measure the force. However, it becomes very difficult to measure the force alone. And therefore, we can actually get the momentum of that object as it is going towards the object. And then we get the momentum of the object after hitting that object during the collision. And therefore, it can help us to find the impulse. So the impulse, the units, as you are aware, it means force is in newtons and the time will be in seconds. So it will be Newton multiplied by the time. So that's what I explained. So for example, let's take for example the impulse one of one object. This object, and it has a change in momentum, meaning that this object M1 has the final velocity, which is given by F1, and the same object has an initial velocity, which is given by I1. And so this change in momentum will give us the impulse for this object, which is given by force 1 multiplied by the time. Take again that we have another object with mass 2, So the change in momentum as well, it will be actually mass 2 multiplied by the final velocity minus the mass 2 multiplied by initial velocity. And therefore, this will be the impulse of the object number 2. And so, if we added the two impulses for mass 1 and mass 2, so we are going to add this one here, F1 times T plus F2 times T, which we have done here. And also we add these changes in momentum. We're going to add this change in momentum for object number 1 and change in momentum with the object number 2, just like what we have done here. And then from here, we will know that time here is common, so we can factor it out. Okay, so what this means is that actually when the two objects hit each other, the forces are the same and they are in different directions. And you notice that if the forces are the same and they are in different directions, it means that, as you know, these are vector quantities. It means that what you get here, F1 plus F2 will be equal to 0. And therefore, that's what I mean here. And so, rearranging this, where you have now the momentum for, you look at the initial momentums we can on one side. So we're going to have the momentum for mass 1 plus the momentum for mass 2. These are initial momentums, will be equal to momentum for mass 1 plus momentum for mass 2. So in other words, if two objects are interacting or they collide, you are going to get the momentum before they collide. You get the momentum for this object before collision. You add it to the momentum for another object before it collides with the other one. And then you get the momentum after the object had hit the other one for mass 1. And then you get the momentum for the object for mass 2 when it has hit the other one, which is the final momentum. So this is actually what is known as the law of conservation of linear momentum, where they are saying the momentum before collision should be equal to momentum after collision. So this is the principle of actually momentum. This is how it came about, where we are saying the momentum before the collision, the sum of the momentum before the collision should be equal to the sum of momentum after collision. In simple terms, what it means is that before the objects interact or collide, get the momentum for one object. And we said momentum is mass times velocity. So it will be momentum, that mass 1 multiplied by initial velocity for object number 1 before interaction. And then you get also the momentum for object number 2 before the collision, meaning that we're going to say mass 2 multiplied by velocity 2. So these two objects are actually going to interact, and therefore we said the momentum before will be equal to momentum after collision. This is a very important concept because in whatever we're going to do, actually, we are going to apply this same principle. And this is a basic principle actually under linear momentum, where we are saying momentum before collision will be equal to the momentum after the collision. So there are different types of collisions, which I want us to briefly go through. There is what is known as the inelastic collision. In an elastic collision, the momentum is conserved after the collision, as well as the kinetic energy is not conserved. So in an inelastic collision, the momentum is conserved before and after the collision, while the kinetic energy is not conserved. For a perfectly inelastic collision, the momentum before will be conserved. It will be conserved, while the kinetic energy will not be conserved for the objects which have interacted or which have collided. And the objects actually, after collision, they stick together, they move together. So that is what is known as a perfectly inelastic collision. An elastic collision is where the momentum and kinetic energy are conserved. Before the collision and after the collision, the momentum and the kinetic energy are conserved. Now, we are going to use now the equations to illustrate what we are talking about on this definition. So for a perfectly inelastic collision, what we are saying is that we have object number 1 with mass 1. You get its momentum before the collision. You add it to object number 2 with mass 2, gets its momentum. So in other words, momentum for object 1 plus momentum for object number 2. That's before the collision. Then this should be equal to the addition of the two masses multiplied by the final velocity, because we said in a perfectly elastic collision, the two masses after collision, they are going to stick together, they are going to move together. So in other words, you just add the masses, and it means that you are going to have a common velocity for the two masses. So that is the illustration for a perfectly inelastic collision. For an elastic collision, we have actually two equations. The first one, as we indicated, is where momentum is actually conserved, as we indicated. So in equation 1, momentum is conserved, as well as the kinetic energy before the collision and after the collision will be conserved. So it will be the same. So this is the kinetic, as you know, kinetic energy is half multiplied mass multiplied by v squared, velocity squared. So it will be conserved. So this is very important because it is different from a perfectly inelastic collision where actually the kinetic energy is not conserved. And so we want to make sense out of an elastic collision. So making the kinetic equation into a linear. So in other words, what we are saying is that to solve this equation in an elastic collision, it means that you have two equations. So to find a solution, you have two equations. It means that you are going to have two simultaneous equations. One is linear, and the other one, because it has a power 2 velocity to the power 2, is a quadratic equation. So you are going to solve one linear equation, and the other one is a quadratic equation. However, at times, you can actually make the kinetic equation, where we're saying kinetic energy is conserved, into a linear equation. And I'm going to go through how we can make this kinetic equation into a linear equation. Instead of using the quadratic equation, we can have two linear equations. The equation number one, where momentum is conserved, and the other one you are going to actually come up with. It's a very simple step actually. And so what we do is that this is the equation which we had, where we said kinetic energy is conserved. So you see that here, the half here is actually common area. So you can cancel half here, cancel it. And what you are going to remain with is this equation, where half has been actually been cancelled. It does not change the equation because it's a common factor everywhere. And after that, you arrange the like terms together. In other words, mass 1 should be with mass 1 even for a final velocity. So in other words, what we have done here is that here we have mass 1 multiplied by velocity 1 for the initial velocity 1. And here you bring this one this side, and it will be negative. Similarly, you take this other equation the other side. And so it means that we have arranged the masses, the momentum with respect to the masses. So mass 1 and mass 1, and here mass 2 and mass 2. Secondly, what we do is that you can easily now, we saw that mass 1 here was common and mass 2 here is common. So you can factor out mass 1. Here, again here you can factor out mass 1. And what you come up here is a difference of 2 squares. So meaning that you know, when you have a difference of 2 squares, you can actually make it in that form, where you can make the addition of this and the subtraction of the same one. Addition of this and the subtraction of the same one. So what we have just done here, we have expanded this. So if you expand this one, this is what you get actually. So in other words, this is what's known as the difference of 2 squares. If you expand this one, you actually get this one. Okay. And so we can as well, from equation 1, you remember we had one equation where there was conservation of momentum and there was also conservation of kinetic energy. So this equation now, equation number 1, you can have it. You do the same what you did here, arranging the masses into their same likeness, meaning that mass 1 should be on its own and mass 2 should be on its own. So you can rearrange them like that. So this same equation, equation number 1, this mass 1, we can bring it here and factor out mass 1. Similarly, this one here, you can bring this side and factor out to mass 2. And you note that what you have factored here is similar to one of these here. So you've seen this one here is the same as this one here. And therefore, you can now divide the two equations. The one for kinetic energy, you divide it with the equation 1 for momentum. So in other words, what we are saying is that we had this equation here, then you can divide it with this equation for equation number 1. And therefore, you note that here, mass 1 is going to cancel mass 1. Mass 2 will cancel this one. This one is similar to that one they have cancelled. This one is similar. This one is similar to this one they have cancelled. And what you are going to remain is the velocity initial plus final velocity, which is equal to final velocity for object number 2 plus the initial velocity for object number 2. So we can rearrange these terms also such that the initial velocities are on their own. And therefore you notice that this one here, the initial velocity can come this side, becomes minus. And then this one, it goes this side, becomes minus as well. And therefore this is F1, F2. Remember this one was positive when it was this side. And therefore it to be positive, you have to put a minus here. So in other words, what this means in physics is that actually the relative velocities, the difference in relative velocities are almost the same but of different directions. So in other words, this is the equation number 2, which you can use with the equation number 1. That is without using now the quadratic equation form. And so today, what we looked at is actually the concepts that pertain to how we can solve linear momentum equations. I hope what we have done today is merely a basic understanding of the equations we'll be using when you will be solving equations in linear momentum. And these are very helpful and very important, because if you miss this step, it means that all the other parts that we are going to use to solve equations will be actually difficult for us. So I urge you to actually you go through again this lesson several times so that you can actually cement the concepts. I thank you.